Okay, more trigonometric integrals. Okay, let's see. So now we got some bounds in here. No biggie, we can handle some bounds. So what do we got? Sine to the 7th of theta times cosine to the 5th of theta d theta. So, our variable is theta. Neat. Cool. So which one do you want to break off? I want to break off a sine, because the derivative of sine is positive, then we don't have to deal with negatives. We have odd powers of sines and cosines. That's good news. That's not bad news. No. Here's our first step. Let's just say, actually, no, I'm going to break off a cosine. I'm sorry. I lied. I lied. Why would I want to do that? Because we're trying to create, that's going to become our du. That's why we're doing this. We're going to do a u sub. We want to create that to a du. So what has a derivative that's equal to cosine of theta? Well, that's sine of theta. So let's change our cosine to the 4th. Right, cosine to the 4th. I'm actually going to do it off to the side. Is the same thing as cosine squared. So it's 1 minus sine squared. So we get 1 minus 2 sines of theta plus sine to the 4th of theta. And we don't actually have to take it all the way, but you're going to end up having to do it anyway. So what do we have? So we have 0 to pi over 2 of sine to the 7th of theta times some junk we're about to pop back in. And so, oh my goodness. So 1 minus 2 sines of theta plus sine to the 4th of theta. Sorry, it's hard to read. I gotta give myself enough room. Now I'd like to just bring this in, and then we can start to do our u sub. So sine to the 7th times 1 is equal to sine to the 7th. Sine to the 7th times 2 sines of theta is sine to the 8th times 2. And then we get sine to the 4th times sine to the 7th. That's sine to the 11th. Woo! Doggy! Let's go! Sorry, my cosine looks all funky. So now let's take our u. Let's let u equal sine of theta. Therefore, du is equal to cosine of theta d theta. The whole point, that's why we wanted to do it. Like I said, we just wanted to make this thing break off. So now we're going to have a polynomial. We're going to be in power rule. That's going to be good news until, I don't want to show you that yet. You know what I mean? So we're going to have u to the 7th minus 2 u's to the 8th plus u to the 11th du. Oh, but there's bounds. We have to plug it in. We got to figure out. So when theta is equal to pi over 2, u is equal to sine of pi over 2, which just equals 1. And then when when theta is equal to 0, well, sine of 0 is equal to 0, so it's just going to stay at 0. So let's take our antiderivatives. So we're going to get 1/8 u to the 8th minus 2/9 u to the 9th plus 1/12 u to the 12th. Fortunately, we're plugging in zeros and ones. So this is going to be 1/8 minus 2/9 plus 1/12 minus 0, right? Oh my goodness. Oh, we got to put those fractions together. I think 72's our guy. That's the one. So that one's going to need a 72. That's 9. So 9 and a 9. So we're going to get 9 over 72. 2 times 8. So that's 16. And then what's 6? So 9 minus 16 is -7. -7 plus 6 is -1. So it's -1 over 72. It's a lot of work for a small number like that. You know what I mean? A lot of work. This is a simple one. Isn't that messed up? As we move on, like, this is a simple problem. These are the ones like on a test. I mean, maybe not the bounds, but you're like, that's what you're going to want. Calculus, bro. What's that? All right. Let's tackle this bad boy. I don't think this one's all that bad. I actually think this one's a little simpler than the last one. It'll be a little less work, I think. Same game. You see an odd power of sine and cosine, you break it off. Just break it off. We got the square root of cosine of x. And this is sine squared times sine of x dx. Boom. There's our du, kind of. You know, that's what we needed so we could start to sub. So that means we want the rest of this stuff. We want it all in terms of just one thing, but we know we can change sine squared. Sine squared is 1 minus cosine squared. So let's do that. And I might write something a little bit different. Uh-oh. Did I write the square root of cosine as cosine to the 1, cosine of x to the 1/2 power? I think I did. Why would I do that? Do you see it? Do you see it? Do you see it? Do you know why? Because we're going to bring it in. We're going to make life simpler. Not simple, but just simpler. So that's cosine to the 1/2 of x. Minus, so what's 1/2 plus 2? Isn't that 5/2? Yeah, so you got cosine to the 5/2 of x times sine of x dx. Is it starting to become a little bit more clear? You're starting to see them now? It takes a few times, but after a bit, I mean, the process is pretty, kind of just remains the same over and over. So u is equal to cosine of x. Du is equal to negative sine of x dx. And once again, I'm cheating and just bringing the negative over to the other side. There we are. We got it. There's our negative du. So now we just go through, we replace everything. So negative integral of, wow. I made it better, didn't I? So there's something to the 1/2. Minus something to the 5/2. And that's u. And then we just end up with our du at the end. I'm going to cheat. And then we'll take an antiderivative. So we get u to the 5/2 minus u to the 1/2 du. Oops. And we integrate. All right, so let's add 1 to that exponent, and then let's multiply by the reciprocal. Let's add 1 to the exponent, and then let's multiply by its reciprocal. We don't forget our plus c, and then we just need to remember, oh, no. We need to replace it back. What was u? U was equal to cosine. So now we could just write it in. It's 2/7 of, let me just write it like this. Just mixing up the notations on you. It all means the same stuff, but we have to make sure we can read it. And there's our solution. Are you starting to catch the pattern? You're starting to see it with odd powers? Cool. All right. So next one, we're going to mess around with some tangents and some secants. It's the same type of game. A little bit different, but it's the goods. And then we'll introduce the derivatives of secant and secant cubed. You won't like it very much. You might want to get them memorized once we show them. So, all right. I'll see you in the next.